Hello engineers, welcome back. In this video, we're going to start a new topic, which is bitwise operators. I hope you're ready. Let's get started. So in this video, we're going to study what bitwise operators are. We'll learn how to convert a decimal number to binary number. We'll see all the different types of bitwise operators, and we'll see why we need to study these bitwise operators. Okay, so let's get started. So like the name says, these are bitwise operators, right? So they operate at a bit level, which means they operate at a binary level. So we studied about different types of operators like arithmetic, logical, relational. So when we say 5 plus 3, we know that this is an arithmetic operator and the result is 8, right? And when we do 5 minus 3, we know the result is 2. So these are arithmetic operators. These are operating at a decimal level. So these are decimal numbers. But when we are talking about bitwise operators, we are talking at a binary level. So in order to better understand bitwise operators, we need to first understand how to convert a decimal number to binary, and then at a binary level, how we can use these operators to perform different functions, right? So let's see. So let's take a simple example to see how to convert a decimal number to a binary number. So let's take an example of 5. So let's say we want to convert the number 5 into binary. So how do we do that? So to convert any number into binary, we simply divide it by 2. And if it's an odd number, it will leave a remainder. If it's an even number, it will not leave a remainder because it is divisible by 2. So how do we proceed? So let's say we divide the number 5 by 2. So what do we get? We get 2 with a remainder of 1. So if we do 2 into 2 plus remainder 1, we get 5. So that's how this works. So we have split the 5 into half, and it is remaining 2 with a remainder of 1, right? And we can further split it. We divide 2 by 2 and we get 1 here with a remainder of 0 because 2 is an even number. And we can go further down and we get 1 divided by 2 is 0 with a remainder of 1. Okay? And we can go one step further. 0 divided by 2 is 0 with a remainder of 0. And now we have the remainders here. We simply do bottom up and we get the binary value. So this is 0, 1, 0, 1. Okay. So this is the binary value of the number 5. Okay. So how do we convert a binary number back to decimal number? That is very simple. So we simply use the power of 2 notation. So we go from right to left and we simply do 2 to the power 0 into 1, 2 to the power 1 into 0, 2 to the power 2 into 1, 2 to the power 3 into 0, and we add them up. So 2 to the power 3 is 8, 8 into 0 is 0, 2 to the power 2 is 4, 4 into 1 is 4, 0 here and 2 here. Sorry, 1 here. 2 to the power 0 is 1, 1 into 1 is 1. So we get 5 back. So that's how we can convert decimal to binary and then binary back to decimal. Okay. Let's take one other example for better understanding. So let's take the number 3 and let's try to convert it into binary. So what do? We divide the number by 2 and we get 1 here with a remainder of 1, and we move on. We do 1 by 2, which leaves a remainder of 0 with a remainder of 1, and then we divide 0 by 2, which gives us 0, 0, and then we do bottom up. So we get 0, 1, 1. So this is the binary value of the number 3. So how do we convert this back to decimal? We simply do 2 to the power 0 here, 2 to the power 1 here, 2 to the power 2 here. So 2 to the power 2 into 0 is 0, plus 2 to the power 1 is 2, into 1 is 2, plus 2 to the power 0 is 1, 1 into 1 is 1. So we get 3. Okay. So that's how we can convert decimal to binary and binary to decimal. Okay. Now let's discuss about bitwise operators. So when we talked about arithmetic operators, we were operating at a decimal level. Now these operators operate at a binary level. So we are no longer discussing 5 and 3. We are discussing binary system like this. Okay. So let's see one by one. So the first operator is not. So let's say this is our number 5. In binary, this is the number 5. So the operator not is a unary operator. It takes only one operand, and it is represented by the symbol tilde. Okay. So when we say not of 5, what it does it flips the switches. So zeros become ones and ones become zeros. Okay. So if this is 5, and the not of this will become 1010. Okay. It's simply a switch. So what is this in our decimal system? This will become 2 to the power 3, 2 to the power 1, 8 plus 2 is 10. So not of 5 is 10. Let's move on to the next operator. The next operator is AND. AND is a binary operator, just like this. Plus is a binary operator, right? It takes two operands and then does a mathematical addition. So AND is similar. It takes two operands. Let's take our two numbers 5 and 3. So this is 5 and this is 3. And if we perform an AND operation, so AND is represented by the symbol AND. And how does this work? So it operates at a bit level at the same position. So if we take this position, 0th position, the resulting number will be 1 if both of the values are 1. Okay. So if both of them are 1, then it's 1. Otherwise, it is 0. So that's how AND operator works. So both of them need to be 1. Otherwise, it's a 0. Okay. Now let's look at the next operator, which is OR. So we discussed NOT, we discussed AND. Now let's see OR. OR is again a binary operator. Let's take our two numbers 5 and 3. And let's do an OR operation. OR is represented by the pipe symbol on the keyboard. So OR is like this. If either one of them is 1, then the value is 1. Otherwise, it is 0. Okay. So here both of them are 1. So the value is 1. Here we found a 1. So the value is 1. 1 here and 0 here. So this is the binary OR operation. So what is the value of this? So this is 2 power 2, 2 power 1, 2 power 0, 4 plus 2 plus 1 is 7. So binary OR of 5 and 3 is 7. What is the binary AND? And this is simply 2 power 0, this is 1. So binary AND of 5 and 3 is 1. Binary OR of 5 and 3 is 7. Okay. And the next one is XOR. XOR is slightly different. Let's see. So if these are my numbers 0101 0011, and XOR is represented by the caret symbol. So this is how it goes. XOR requires variety. You can just remember this word. XOR requires variety. If there is variety in the equation, then it is true. Otherwise, it is false. So let's see sequence by sequence. So if this is the equation, here both of them are 1. So there is no variety. So this will be 0. Here 1 is 0 and 1 is 1. So here there is variety. So whenever there is variety, this goes to 1. Again, here there is variety. So this is 1. Here both of them are same. Then it is 0. So this is how XOR works. So what is the decimal number of this? So this is 2 power 2, 2 power 1. So 4 plus 2 is 6. So the XOR of 5 and 3 is 6. Okay. Now let's move on. Let's do left shift. Left shift is interesting. Left shift and right shift are again unary operators. So this is my number 5. And if I want to do left shift of 5, so left shift is represented like this, and we need to give a number left shift by how many bits. So usually we do left shift by 1. So when we do left shift by 1, what does it mean? It means move every bit to the left. So the resulting number will be like this: 0, 1, 0, 1, which means that everything is left shifted by 1 bit like this. And because we cannot leave this empty, we will append a 0. Okay, we have appended a 0. Append 0. So this is the resulting number of left shift. So what is this number? 2 to the power 0, 1, 2, 3. 2 to the power 3 plus 2 to the power 1. So this is 8 plus 2. This is 10. So left shift of 5 by 1 bit will give us our decimal number of 10. Okay, so we are shifting the bits by 1. Now let's discuss right shift. Right shift is like this. So this is my number 5, and right shift is represented by 2 right arrows. And like you would expect, we need to right shift the bits by 1. Okay, so it is something like this. So now we have 0, 1, 0, 1. Okay, and we prepend a 0 here. In the previous case, we appended a 0. Here we prepend a 0. And here you will notice that when we have right shifted the last bit, it is coming out of the memory, right? Like this doesn't exist practically. Okay, so we have done a right shift, which means that we have essentially eliminated the last bit, or we can call it the least significant bit or something like this. So in this way, we have right shifted every element, and when we do right shift, the last bit is lost. Okay, that's how we do right shift. So what will be the resulting number? This is simply 2 to the power 1, that is 2. Okay, so the right shift of 1 for the number 5 is 2. So that is right shift. So we've discussed left shift and right shift. So before we discuss why we need to do all this, why we need to learn all this, let's see all these operators in code. Okay, let's go to our VS Code, and I've created a new file called Bitwise Operators, and let's see one by one. Okay, so let's take our number, which is 5. So this is our number 1, which is 5, and num2, which is 3. Okay, now let's do one by one. Let's calculate the result. Actually, we don't need a result variable. Let's do a cout directly. Let's do 5 and 3. And this will be calculated like this. So 5 and 3. So if we put a double AND here, this will become a relational operator, conditional operator. But if we use a single AND, it is a binary and bitwise operator. Okay, so this is 5 and 3, and we are expecting the value 1. Okay, let's see. Expected unqualified ID. I think probably we'll need to save it in a variable. Let's see if I do result equal to num1 and num2, and I simply put result here. Yeah, we got it. So 5 and 3 is 1. Okay, let's do something else. This time let's do 5 or 3. Or is represented by the pipe symbol, and let's calculate or. This time we are doing or. Let's see. So 5 or 3 is 7. Is that what we have? Yes, this is 5 or 3 and this is 7. So we got the answer. Let's see the next one. This time let's do XOR. XOR is represented by a caret symbol. And let's see 5 XOR 3. 5 XOR 3 is 6. So this is what we had. 5 XOR 3 is 6. Now let's do left shift and right shift. So let's do cout left shift 5 by 1 bit. So we have num1. Actually, let's save this in some other variable. Result equals num1 left shift by 1. And then we can print the result. Here we go. Let's see. So left shift 5 by 1 bit is 10. And that is what we got, right? We got left shift of 1 is 10. So that is how it worked. Let's do right shift. Right shift of 5 by 1. Let's calculate. Let's run it. Right shift of 5 by 1 is 2. And we got 2. So that is how bitwise operators work. Okay. So you can take different examples. I used 5 for our video. You can try the same thing with 2 and see how it works. Now let's see why we need to learn all this. So there are some specific use cases when it comes to dealing with integer arithmetic. And when we use bitwise operators, they are just faster than the normal operators, because these bitwise operators are operating at a hardware level. And when we are doing bitwise manipulation, we are essentially reducing the CPU cycles, and these are happening at a constant time usually. And that's why in some specific cases we use bitwise operators. So to give you a better appreciation of the bitwise operators, so I got a code online for comparing the same operation when done with bitwise and when not. So without going much into detail about how this works, I'll just show you what we're doing here. So this is our main function. So we have a vector nums, and we are pushing elements into nums, and the idea is it fills the vector with pairs of numbers, and at the end we will push one number which is unique. So there are a bunch of pairs and one unique number, and the question is to find that unique number. Okay, so we can use it, we can do it in two ways, with using bitwise operators and without using bitwise operators. So there are two functions: find the unique number with XOR and find the unique number with set. Okay, and the code is doing a clock timer. So before executing this function, we are calculating the timestamp. After executing the function, we are calculating the timestamp, and we are getting the milliseconds out of it, and we are printing the milliseconds. Okay, so we are repeating the same thing for two functions. One function is doing with bitwise, another function is doing with a set. Okay, so when I run this, you will see the difference. Let's run it again. So there is some problem here. Let me remove the temp file and let's run it again. Right, so you can ignore the warnings for now, but see this. unique element finding with XOR for 1 million elements. So those are 1 million elements in the vector, and XOR is taking 12 milliseconds, but set is taking almost 400 milliseconds. Okay, if I run it again and again, you can see the difference. So this is taking 10 milliseconds, this is taking 400 milliseconds. Let's run it again, and you can see 14 milliseconds, 400 milliseconds. So there is massive difference in terms of performance. So both of them are taking the time complexity of O of n, because both of them will look at each number in the vector to determine if it's unique. But when we are using XOR, it is taking much lesser time because it is operating at a hardware level. Okay. So I'll leave this code in the GitHub for you to analyze. But this is how, in some particular use cases, bitwise operators can be of help. Okay. So think of it like another technique, just like how we discuss prefix sum, how we discuss sliding window, two pointers. So it's like another technique, another trick in your bucket, so that when the time comes, you know that bitwise operators help. Okay, and that is how we can use bitwise operators to achieve faster performance. Okay, and I want to leave you with one exercise. So I deliberately did not code this one and not 5 in code. I want you to do this. So we discussed that the not operator simply flips the switches, right? 0 becomes 1, 1 becomes 0, and 8 plus 2 should give us 10. So the not of 5 is 10 in our calculation. I want you to run this in code in C++ or any language and see if you get 10. And I want you to kind of think through it and Google about it. The obvious thing is that you will not see 10, you will see something else. And I want you to tell me what do you see and why you think that is. Okay, so I'll leave that to you as an exercise. So that will be a very interesting use case when you discuss about things like signed integers and unsigned integers. So I want you to explore that area. But having said that, I think we have covered everything for this video. So let's pause here, and I will see you in the next one. Thank you so much for watching, guys. If you have any questions, you can ask me. And please don't forget to like the video. Please don't forget to bookmark the playlist and share it with your friends. Please subscribe to the channel if you haven't already. And I will see you in the next one. Cheers.